All of the different types of stars in the sky are kind of like a family. There are similarities among them, but there are also big differences. In the upper image, you see a progression of color from red to orange to yellow-white to white to blue-white to blue. These are the different colors that stars can shine. Below each star is a letter indicating how they are classified. For example, the sun is a G star, meaning that it is yellow. If you reverse the order you see here, there's a dorky sentence you can learn to remember the letters in order. The letters, from right to left, are O, B, A, F, G, K, M. And the dorky sentence is O, be a fine girl or guy, kiss me. In the lower images, you can see illustrations of some of the other situations that stars can exhibit. In the first image, you see one star orbiting around another star. The amount of light we see varies over time, as you see in the curve on the bottom. When we observe a star dimming and brightening on a regular interval, we can determine that it may have another star orbiting it. Whether we see both stars or only one, we can see a change in the amount of light that reaches us over time. These stars are called eclipsing binaries. In the lower middle image, we can see a small companion star orbiting around with a larger friend. Most stars have a friend that they orbit around with. Our sun doesn't have a companion, but most other stars do. If there are two stars orbiting one another, they are called a binary star. If there are more than two, they're called a multiple star system. In the final image on the bottom right, you see another light curve, where brightness varies over time. This can indicate that the star is a type of star called a variable that pulsates over time, getting dimmer and brighter over regular intervals. On the right, there's a binary star called Albireo. To the naked eye, Albireo looks like a single star, but with binoculars or a telescope, it's actually two stars, one blue and one yellow. In the image on the left, you can see how they orbit one another. In the case of a star with a planet, the planet orbits the star because one star is so much more massive than the planet. But with a binary star, they orbit around their combined center of mass. This is technically true of the star-planet system as well, but the center of mass is within the star. With two stars, the center of mass is usually between the stars, closer to the larger star. In these systems, once you know the distance between them, A, and the time period their orbit takes, P, you can find their combined mass, mass of star A plus mass of star B. Here's a sample problem. If you have a binary system with a period of 32 years and an average separation of 16 AUs, what is the total mass of the system? The equation says that the mass of A plus the mass of B equals A cubed divided by P squared, where A is the distance between the stars and P is the orbital period. So the combined masses equals 16 cubed divided by 32 squared, which gives us an answer of 4 solar masses. Now, if in this example star A is 12 AUs away from the center of mass between them, and B is 4 AUs away, what are their individual masses? Well, based on the 12 AU and 4 AU distances, that gives a ratio of 12 to 4, which can be reduced to 3 to 1. Since the total mass of the system is 4, which is 3 and 1 together, that tells us that B is the larger star at 3 solar masses because it's closer, and star A is the smaller one at only 1 solar mass. Remember, the larger star is always closer to the center of mass. Hopefully, you can at least kind of follow the math here. This is not a super important one of the equations we'll be working with, but it's important to see how we can figure out the masses of stars. Obviously, we can't fly to a star and weigh it on a scale, but since most stars have a companion, we can use this equation to find out how heavy they are. Mizar and Alcor are examples of binary and multiple star systems. To the naked eye, Mizar and Alcor each look like one star, in the second to last position in the handle of the Big Dipper. They were called the horse and rider by early Arab astronomers. However, with a small telescope, you can see Mizar as two stars, called Mizar A and Mizar B. However, Mizar A, Mizar B, and Alcor are all each binary stars. So what looks like two stars to the naked eye is actually 6 stars that orbit around each other. When a naked eye star can be determined to be 2 stars with a telescope, we call it a visual binary. The star Mizar is called a visual binary, meaning that you can split it into 2 when you look through a telescope. Once spectroscopy was discovered, it was determined that each of these stars had a companion that could be detected by looking at the spectral lines from the stars over long periods of time. You cannot detect these companions visually with just your eyes. Here you see an example of how this works. Here's an image of the star Capella and 2 of its components. Can you see how the pair of stars on the left is slightly shifted as compared with the pair on the right? This is detected by spectroscopy, looking at whether each star is red-shifted or blue-shifted at different times. In the spectral line images, look at the motion of the stars compared to the eyeball. In the first, third, and fifth image, there is no red or blue shifting seen, as the stars are moving to the side with respect to the eyeball. However, in image 2, can you see that A is approaching the eyeball as B recedes away from it? Then, in image 4, you can see the opposite. Can you see the lines shifted to different positions? This is how we detect a binary system when the system is so far away we can't separate the 2 bodies separately, or they are too close together to see the gap between them from Earth. Here is a binary star called Algol. It's called an eclipsing binary. Algol's name literally means demon star. Early people thought this star was possessed by the devil because it varies in brightness over time. The reason why this occurs is due to the fact that we see the system from the side. Sometimes we see this setup on the bottom right, where both stars are side by side. This scenario produces the brightest view of Algol. Other times, we see the situation on the top left, where the brighter blue star is in front of the dimmer yellow star. This produces the small decrease in brightness. The dip is small because the brighter star is in the front and only the dimmer star light is blocked. However, at other times, we see the dimmer yellow star in front, blocking the light from the brighter star. This produces a large decrease in brightness. When this pattern continues to repeat, we can assume we probably have a binary system. Here's a graph showing the light curve of a type of a variable star called a Cepheid variable. These stars are called Cepheids because the first example found was a star, Delta Cephei, in the constellation of Cepheus. This star was discovered to pulsate over time by Henrietta Swan Leavitt, an American astronomer. As you can see in the graph, as time passes, the luminosity of the star increases then decreases. The radius of the star itself actually changes over time as well. The time period over which the star pulsates is directly related to its brightness. That means that these type of stars can be used as standard candles. This means that if we know how bright an object should be, and we compare it to how bright it looks, we can actually do a calculation to figure out how far away the object is. That means if we can observe a Cepheid variable in another galaxy, we can actually figure out how far away the galaxy is. Remember that we have already discussed another way we can tell distance to stars, parallax. If you hold up one finger in front of your face with one eye closed, when you switch eyes, your finger seems to jump to another location. The reason why is that your eyes are angled slightly differently, and you're seeing your finger in front of a different background. With stars, it works very similarly. At one time of year, say July, As you look toward a nearby star, you see a certain background behind that star. 6 months later, looking toward that same star, you see it with a different group of stars in the background since Earth has moved to the other side of the Sun. This method works only for nearby stars, as the shift the star makes looks smaller and smaller the farther away the star is. At some point, no shift is detectable, meaning that we can't calculate the distance. There are additional ways to calculate distance. First, you need to know the conversion factor to change parsecs to light years and vice versa. A star that shows a second of parallax is a parsec away. Remember, a degree is divided into 60 minutes and a minute is divided into 60 seconds. So a second of parallax is a really small amount of shift. There are 3.26 light years in a parsec. There are a couple of equations that we can use. The second one we'll come back to in a moment, but let's look at an example using the first equation. Altair is a star that has a parallax of 0.194 arcsecond. How far away is it? The equation says that distance measured in parsecs is equal to 1 divided by the parallax. All you have to do is take 1 and divide it by the given parallax, 0.194. And that gives us an answer of 5.15 parsecs. Now, if I want to know how far that is in light years, I use the 3.26 conversion factor. The number of light years is equal to the value 3.26 multiplied by my number of parsecs, in this case, 5.15. And I get an answer of 16.80 light years. Make sure as we work through these problems that you are typing them into your calculator as well to check your answers. As different brands of calculators are programmed differently, sometimes you have to type the information in different orders. It's important to know how your calculator works so that it will give you the right answers on your assignments and tests. In addition to distance, luminosity or brightness is another very important quality of a star. There are two different ways to measure a star's brightness. One is called apparent magnitude. If I say that you appear tired, you may or may not be tired, but you look tired to me. Apparent magnitude is a measure of how bright a star looks to us here on Earth. The Sun has the highest apparent magnitude because it's quite close to us, but in reality, it's pretty dim compared to many other stars. Absolute magnitude is a measure of how bright a star actually is. We compare the stars as if they were all 10 parsecs away. Compare the pairs of images. In the top pictures, we see that from Earth, the Sun looks very bright, while Arcturus looks much dimmer. In actuality, though, the Sun is much dimmer than Arcturus. The Sun only looks so bright to us because it is so much closer than Arcturus. Here are several other equations that compare luminosity and distance, luminosity and mass, stellar lifetime and mass, and luminosity, radius, and temperature. Let's look at how to use each of them. Here's another sample problem. The star Polaris is 132 parsecs from Earth and has an apparent magnitude of 2.5. What is the absolute visual magnitude? In this equation, little mv is the apparent magnitude, big MV is the absolute magnitude, and d is the distance measured in parsecs. Plug in the 2.5 for little mv and 132 in for the distance. A calculator tells you that log of 132 is equal to about 2.12. Moving big MV to the right and the other numbers to the left gives us that the absolute magnitude of Polaris is negative 3.1. Since the brightest star in our night sky is Sirius at magnitude -1, if Polaris was only 10 parsecs away, it would be so much brighter. Remember, the larger the magnitude number, the dimmer the star. So stars with negative magnitudes are very bright. This time, we're looking for luminosity of a main sequence star that is 4 times the mass of the Sun. We haven't talked about what main sequence means yet, but we'll get to that later in this unit. The equation states that L equals m raised to the 3.5 power, where L is luminosity and m is mass in solar masses. So L equals 4 raised to the 3.5 power, which is 128. That means that a star that is only 4 times heavier than the Sun is actually 128 times as bright. For the next equation, we're looking at how long a star lives. Let's keep looking at the same star that is 4 times the mass of the Sun. This time, the equation says that Greek letter tau equals 1 divided by m raised to the 2.5 power, where tau is the lifetime of the star and m is mass in solar masses. So tau equals 1 divided by 4 to the 2.5 power, or 1/32. So that star that is 4 times heavier than the Sun will live only 1/32 as long. In the next equation, we're comparing L, which is luminosity, to R, which is radius, and T, which is temperature. Suppose a star has 10 times the Sun's radius, but only half its temperature. How luminous is it? In the equation, the asterisk is representing the star, and the circle with a dot in it represents the Sun. This equation looks kind of scary, but it's really not that bad, as we're really only looking at 3 numbers. The 3 numbers are the 3 ratios comparing the star to the Sun. The question asks for luminosity, so we don't have anything to plug in there. We leave that alone. For the R part, the radius of the stars, we know that the star is 10 times bigger than the Sun. So the ratio is 10 to 1. 10 for the star, 1 for the Sun. We plug those values in for the R's. For the T part, the temperature of the stars, we know that the star is half the temperature of the Sun. So the ratio is half, or 0.5 to 1. 0.5 for the star, 1 for the Sun. We plug in those values for the T's. Now we solve. 10 over 1 squared is 100. 0.5 over 1 to the 4th power is 0.0625. Then multiplying those two together, we get 6.25. That means that the star is 6.25 times brighter than the Sun. In this final equation, we're looking at a variation of an equation you probably learned back in middle school relating distance, speed, and time. This time, we're trying to do the same thing with wavelengths of light. We want to be able to figure out how quickly different objects are moving compared with us. VR is radial velocity, or speed. This upside down Y thing is a Greek letter L, which is called lambda. Lambda is measuring wavelength, which is a distance. C is the speed of light. Here, we're looking at Doppler effect again, trying to determine, based on the wavelengths of light observed, whether objects are moving toward or away from us and how quickly. Remember, the red or blue shift tells us which is which. Let's look at one final sample problem. Suppose the laboratory wavelength of a certain spectral line is 600.00 nanometers, and the line is observed in a star's spectrum at a wavelength of 600.10 nanometers. Find the velocity of the star and determine whether it's coming toward you or receding away from you. Now, this equation might look a little scary too, but it's really just a division followed by a multiplication. Velocity equals change of wavelength divided by lab wavelength times the speed of light. So VR is what we're looking for. The wavelength change we find by comparing the wavelength now with where the wavelength ought to be. The wavelength changed by 0.10 nanometers. The lab wavelength is given as 600. We divide those, then multiply by the speed of light. And we get our speed, which is 50 kilometers per second. Since the change in wavelength, meaning this term here, is positive, meaning that the lab wavelength to the new wavelength is a bigger number, that we went from a smaller number to a bigger number, that means positive. That number has increased. That means that the star is traveling away from us. If it had been a negative number, if the number had gone from bigger to smaller, that would tell us that the star is coming toward us. The book goes over each of these problems and gives you a few more samples in the chapter review. Make sure you understand how to apply each equation. Visit me in office hours if you'd like to go over a few more, and you can always call or email if you have a specific question as you work through problems.